All right. Hi, everyone. Okay, so today I thought we would review some of the basic concepts in computer science. I know that um, people may be taking this course in different years. Last year, I think most of my students were sophomores. There was at least one freshman and at least one junior. Um, so I want to be able to discuss the topics throughout the course freely, but I think some of the concepts may lack imperative or importance unless you understand some of the underlying problems that certain concepts are used to describe and facilitate a solution for. And so with that in mind, that's kind of the spirit of today's class. I apologize for getting the video uploaded late. I was working on extending the notes, and there's still more work to do, so I apologize that you're taking this class this semester and not a year from now, assuming I'm teaching this again, when the notes will be a little more refined. So that was unfortunate on your part, but I applaud your eagerness to get this course over with. Okay, so let's jump into it. Whenever I need a whiteboard, I'll jump back in, and we'll come back to this. So, okay. So the first concept that I want to cover is data structures. And so I know that we'll discuss trees and graphs in this course, but I want to go ahead and just give a quick overview as well. Right? So what is a data structure? Okay, so data in the programming world falls into one of two categories. So there's primitive data types, which are int, float, double, string, bool. In JavaScript, function is a primitive data type, although it's already kind of a complex data type if you look at it that way. And it may be possible that some other languages specify some other primitive types. I was doing this from memory, so my apologies if I left one out. And so, oh yeah, byte, I guess, and byte arrays and so forth, I guess would count. But okay, so setting aside those additional inclusions that ought to have been there. These are the basic types, the building block types, and then modern programming languages allow for complex data types. So you can group them together under a single umbrella variable, if you will. And so the example I have here is a student, right? So students, they would have a name, which would I left that off because C doesn't specify a string type. It has a character pointer, and I was kind of waffling a little bit on whether or not to include that. But you can include an integer student ID value, or possibly a long, an integer birth year, and an integer graduation year. So all of these are attributes that would go into the description of a student. Right? And so obviously the list isn't exhaustive. Like I said, there would be a name, there would probably be a birth month and a birthday as well. And depending on the language that you're using, you might choose to use a date to represent the student's birth date, and a date to represent the projected graduation date, and maybe a reference to a major or something like that as well. So the struct is nice. It allows you to sort of group data like that, and it's what's available to you in C. But in C++, in Java, and in Python, we have what's known as a class. And so a class provides everything that a struct does, with the added benefit that you can also define methods that will act on that data or perform arbitrary actions if that's really what you want. But if your methods aren't related to the data, then it's very poor design, and you just need a little bit more programming practice. But we can assume that in general the methods will have something to do with the data that is present. So one example of a method that you might include is a toString method. So if you want some string representation of a student, then you would have it take a look at the data and then come up with some reasonable output for it. So one example might be to put student ID colon and then the student ID number and then comma student name and then last name comma first name and so forth, or something like that. Just some sane representation of it. So the toString method acts on the data that's stored in the student. And so this is both the struct and the class are complex data types, but neither one of them is really a data structure. So whenever we speak of data structures, we're talking about something that is very specifically a computer science concept. So it's the way that multiple data points relate to each other. And so the first example on this is a linked list. So a linked list gets its name from the links in a chain. Each chain holds on to the link that follows. And in that regard, whenever we think of a chain, it actually goes in the other direction as well. So it holds on to the link that follows as well as the link that precedes it. So whenever we think of a linked list and it only referring to the one that follows, it's a singly linked list, and whenever it goes in both directions, then it's a doubly linked list. And there's a few phrases that are associated to linked lists. So there's a head and a tail, and so in a doubly linked list, we're allowed to start from the end and work our way back. In a singly linked list, we have to start at the head and work our way forward. We can only move in that one direction. And you'll notice that in the example that I've given, the double list, it separates the concept of the node itself, so the chain link, the actual cog in the machine, from the structure itself. And I think this is really more appropriate because the actions, so if you were to use classes instead of structs here, then the actions would act on the list and not necessarily on the node itself. So I think that makes sense. But it's also possible to just represent the list as a reference to the first item in the list, or a reference to the last item in the list. And then I've gone ahead and given an example method of append, and you pass in the list and then the new item, and it in the case that the list is empty, then that new item is both the head and the tail, and then in every other case the tail gets a reference to the previous item, which was the previous tail, and then the former last link in the chain, if you will. And then the list gets a new tail, which is the new tail. Yeah, and then I should have updated the actual reference to list.tail as well. So that was a mistake as well. Yeah, let me fix that so that it's correct. Let me show you what I mean. So I should have also done list tail equals new tail. So the notes that I post online will include that update. So my mistake. Okay, so one of the things that I want to strive to do as we go through the class, and as particularly this review, is to give you some examples to hold on to whenever you're thinking about these items. So a linked list conceptually is not that difficult to understand, but the question is, why would we use one? And so, in general, whenever I think of a list or a linked list, anytime that I think of discussing a chain or something where things fire in succession, and typically in a prioritized succession, it starts with a particular thing and then it passes on to the next one and so forth. If I would describe it as a chain, then I think of a linked list. So the event chain that handles keyboard input is one example of when you would use a linked list. So there may be, like, if you imagine pressing Control C and Control V whenever you're in a text editor. So C and V are both printable characters. It's both of them represent characters that you might actually want to print. Whenever you have highlighted text, you might want to replace the highlighted text with either one of those. But the control combined with the control key combined with either one of them has a special meaning. You want to do something else. You want to either copy it to the clipboard or paste whatever's on the clipboard into wherever the cursor's current position is. And so the text editor, or the text box, or whatever input element you're looking at, would want to consider that special action rather than just the key itself. And so you would have a series of listeners where one of the earlier ones checks for that special case to see whether or not one of the control keys, either shift or control or alt or whatever, is held down while you're pressing that particular button, and whether something else needs to take priority and basically act as though the key was never pressed. So in that case, the event handler chain would short circuit. So one of the higher priority handlers would take a look at it, and it would realize that it's something that's supposed to happen with the clipboard, and then it would call something like prevent default behavior, and the rest of the chain would be short-circuited. But in the normal case of events, that special handler doesn't need to do anything, and so it just forwards it on to the next item in the chain. So whenever you have a series of event handlers, you can think of them as being represented by a linked list. So the first item in the list needs to take a look at it. It probably does nothing, and then it passes the responsibility on to the next item in the list, and so forth. And so that's kind of the purpose of a linked list. So it's not just this ancient programming concept. It is used pretty regularly, just not whenever you're first developing, aside from homeworks and stuff like that. Okay. So the next item is a queue, the next data structure. And so a queue, if you didn't grow up in the United States, a queue is like a line at a shopping, at a supermarket. Whenever you're checking out, you queue up. Here we call them lines, and that's unfortunate since it means that queue is kind of a foreign word to us at first. But it really is that simple. And so if you think of it in the shopping checkout line example, then there's typically two methods that are associated with queues. There's enqueue and dequeue. And so enqueue is whenever you enter the line. So programmatically, when you enqueue something, you're sticking it at the back of a line. And then whenever you dequeue something, you're removing it and going to the next one, right? So the shoppers themselves in this example would be enqueuing themselves, and then the checkout clerk would be dequeuing them. So they scan all the items, the customer pays for whatever they have, and then they leave, right? So that's the operation that happens as part of the dequeuing action. And so I think that's a fair example of what you would be doing programmatically. So you could actually use a linked list to represent a queue. Right? We talked about how it had that sense of ordering where you go in first and you go on to the next item and so forth and so forth. The difference here is that whenever you would implement the queue using a linked list, like you could use a linked list to do that, you have to make sure to remove that first element. So you would perform a few operations. You would take a look at the head of the linked list, and then you would go to the next item in the list, and you would say, okay, there is no previous element, you are now the head of the list. And then at that point, the former head, the customer that was just processed, is free to go. They've been cut free, they've been severed from the queue. And so that is dequeuing. So NQ and DQ. Stacks, the analogy that I was given whenever I learned, and it stuck with me all these years later, is like a stack of plates. So whenever you're taking the plates out of the dishwasher and you're putting them in the cupboard, the easiest way to do it is to just place the next plate on top of the previous plate. And so it has this effect that whatever the oldest plate in the stack is basically the least used. You very rarely get down to that last plate if you're washing your dishes regularly, or I don't know, perhaps that's a lack of awareness with my audience where maybe you guys don't have as many plates at this point in your life, but in theory, if you had a sufficient number of plates, then you wouldn't get down to it. But the concept is distinct from that, right? So you push the next plate onto the top of the stack, and then whenever it comes time to eat or to use that plate, you pop, whenever the pizza arrives, right? You pop the plate off of the top of the stack, and then you use it. And so it's exactly that, where new items are placed on top, and then whenever you need to remove an item, it is removed from the top. So you'll see in your books queues referred to as FIFO, first in, first out. So those are like the shopping lines. And then stacks are referred to as FILO, first in, last out, where the dish that was in the cupboard the longest is the last one to be used. Okay. So the next example of data structures are hash tables, dictionaries, and maps. So these are all synonyms for the same concept. You have a thing. You have a storage array, basically. They're all glorified arrays, essentially, and you want to be able to look for a particular item instantly, right? You have the item. I just want to know where it is. So this is the structure that solves that problem. And so it does it by means of a hashing function. So imagine you set up a rule for a string, right? So you could use a string as the key. So if the data represented students, again, then you could use either the student ID as the lookup value, or you could use the student name so long as it was consistently done. And then you add up the ASCII character code for each of the letters of the name, and then you perform a modulus operation or whatever, where you divide by the number of available slots in the hash table, and then that is the address of it, and you resolve collisions accordingly. Okay, so maybe that did make a lot of sense. So I have tried in the notes, as you'll see, to come up with another example of what this concept is of trying to use the data and create a function that defines some specific location where you can find what it is that you're looking for in that data set based on the key. So here, the example that I give is a group which meets secretly, right? So either so in my head I was thinking of like if you had a resistance group in France during the time of Nazi occupation or whatever, and they wanted to come up with a secret meeting location where they didn't have to worry about using the same building over and over again. They just used a series of rules to determine where they were going to meet up, and that way none of them had to talk to each other to figure out where they were going to meet or communicate it. You just define the set of rules in advance, and then you use those to figure out where it is that everyone is going to be that night so that you can discuss La Resistance. Right? And so in this example, if it rains between a given hour, then you would meet at location A. If there's a car accident, whatever, before a certain time, then you would meet at location B. And then if both of those things occur, then that's the same concept as a collision in our hashing function. And then you would have certain rules that would resolve that, right? Like one of the locations would take priority or some other thing would happen. And so in this case, your hash table, or in the case of La Resistance here, your hash table is the size of the number of available locations where you can expect to find the group, or expect to find your data, whatever. And the function is what gets everyone to the same location. So everyone looks at the same key, right? In this case, the key is whether or not it's raining, whether or not an accident occurred, whether or not they set fire to the previous night's location or something like that. Then that would all contribute to the key, to the hashing function, and it would help to determine where to go. Right? So it's perhaps more complicated example than the original concept, but I think it also lends a bit of corporal sense to the concept. Okay, so the next item is trees and heaps. So trees are easy enough to understand, and heaps I'm probably gonna have to switch, or I would like to switch to the whiteboard for that one so that you can kind of get a better sense, right, of what it is that I'm saying. So a tree is a little like a corporate structure or an executive structure, where you have a CEO at the top, and assuming that they don't have some board of directors above them, then the CEO is the guy, they're the chief, right, or the girl in this case, right. And so she rules over everyone else. All of the other chief executives report to her, the chief financial officer, the chief information officer, and so forth. And then each of these individuals will have their own departments that run underneath them. They'll have VPs and directors or whatever. And they may also have secretaries or administrative assistants or whatever that work directly for them as well. And so the directors and the VPs will have people underneath them and so forth. But the chain ends eventually, right? So eventually they get to developers or janitors or I imagine there are other jobs than developer. No, all right, like the support and marketing and whatever else, right? And so, but eventually you reach the people that don't have anyone reporting to them. And so in a tree, or whenever we speak of the data structure of a tree, in this example, the people that don't have anyone reporting to them would be leaf nodes, and so there's no requirement the leaf nodes be a certain distance from the CEO. Like the CEO themselves may have individuals that don't have people reporting to them. For example, if they have an assistant, then that assistant likely reports directly to them, and they don't have anyone reporting to them in turn, as opposed to the other executives who would have people reporting to them. So the non-managers are all the leaf nodes. Everyone in between the non-managers and the CEO is an interior node, and then the CEO would represent the root of this tree structure. Okay, so a heap is a special kind of tree structure. And so it is a tree structure that has either some maximal or minimal property. So in the corporate example that we just gave, if hierarchical importance was based solely on tenure at the company, then no one would ever report to someone that that had worked at the company for less time than they themselves had. Right. So no company operates like this. They always hire individuals for the position that they're looking for, or they may promote from within, but they'll do it based on a wide array of criteria rather than just how long the individuals managed to not be fired from the company. But if we did take this as our example, then in this example, our heap would have the CEO as the most tenured employee, and then underneath them would all be underneath her would be all of the people with in their given departments with the most experience, and then so forth and so forth on down. And so one of the things that I want to point out, and I'll show on the whiteboard, is that this doesn't necessarily mean that being close to the root, in this case, being close to the CEO, means that that you have more tenure than someone that's lower on the totem pole, right? So if you consider a developer that will have worked at this company for 25 years or whatever, then the CEO may have an assistant that's only been at the company for 5 years. So in the tree, they're at a higher level because they report directly to the CEO, but the tenure is less than perhaps someone that's lower on the tree. And so let me draw an example real quick, and then we'll switch back to the notes here in a second. Okay, so okay, so CEO, 35 years. Right. So in this example, you have the developer that's been here for 25 years. The CIO, there's some middle management here that's all happened within a 5-year span. And then the CFO has been there for 30 years, and the administrative assistant will have been there for 5 years. So this this position is filled by someone that's been there for less time than someone that's at the very bottom of the tree, but the heap condition is still satisfied. This is a maximal heap. You can have it where it's the other direction, where there's some minimal heap, right? So if you were performing triage at a hospital, then you would rank the patients by the number of minutes that they have to live, and the individual that has the least amount of time is going to be at the top. They're going to have the priority for getting into the ER as opposed to everyone else. Right? And so in heaps, there's no guarantees among siblings or anything else, right? So this individual, could have been there for just 10 years. The CFO could have been there for just 10 years. Like if the CEO did that job for 25 years and then finally the company got big enough and they were able to hire someone else to do all the financial stuff, then this individual could still definitely outrank the lowly dev, but it doesn't matter. The heap condition is still satisfied because the individual higher on the tree has more of whatever it is that you're measuring for. In this case, it's tenure at the company, but it could be something else. So a maximal heap has whatever it is that you're using for your comparison criteria, with the largest value at the top, and then every time there's a parent-child relationship, the parent has more of whatever it is that you're measuring, in this case tenure. And then a minimal heap is the opposite, where the individual with the least of whatever it is you're measuring is here, and then every parent-child relationship satisfies with the condition that the parent has less of whatever, in this case, right? And so heaps will typically be balanced as much as they can. So this satisfies the heap condition of the parent-child relation, but it doesn't necessarily satisfy the balanced condition. So whenever we discuss memory allocation, which we'll do here in just a little bit, we'll speak of memory being allocated to the stack and to the heap, and the heap, whenever it's being managed by the operating system for a program that's running in user space, it will typically be balanced. So maybe we'll come back and I'll show you another example of that whenever if we talk about memory allocation in that much depth. But okay, let's jump back and we'll move on, and we might come back to this, or we might discuss heaps later. We don't use them a whole lot in this class, but I think they're interesting in that you can kind of use it to sort out certain prioritization and stuff. But it's also kind of obscure. You have to be very specialized to actually need to use it. But hey, gathering knowledge, understanding that certain things can be used in certain situations, it never hurts to know more. Okay. Okay. So that was the heap condition that I was trying to demonstrate over here. But again, typically it would be balanced as well, where it's essentially a full tree, or as close to as you can get. But if we ever have need, we'll come back and discuss that. And then the last data structure that I guess we'll discuss right now is graphs and lattices, and these are basically the same thing. And so a graph may have, so where a tree has the condition that every node has no more than one parent, with the root being the exception that has 0 parents, the root is root, and then every other node has one parent and it goes up. A graph or a lattice can have, it doesn't even necessarily have that parent-child ordering relationship. So a lattice is a little bit like a tree in that you can think of them as having parents. So for anyone that studies abstract algebra in the future, they use lattices to represent groups and subgroups, where basically everything is kind of derived from the symmetry group, which is the number of permutations that you can shuffle a set of finite size. So if you had 10 elements, then the symmetry group would be the number of different orderings that you can have on those 10 elements. And then it would have certain numbers of subgroups and so forth, and the subgroups would derive from other groups. But rather than it being like in the way that we have programming, hierarchical tree-based derivation, it would be more of a lattice structure where a particular subgroup can actually have multiple parents. So at the top, the granddaddy of them all would be the symmetry group on that number of elements, so on 10 elements, and then at the bottom, it would be the modulus group. I'm trying to think Z1, basically, where it's just a single element that doesn't really do anything, but it essentially represents one, conceptually, where it's this identity, and so everything essentially filters down to that one at the end, and so the relationship is managed as very non-tree based way, but it's still hierarchical, so that would be a lattice, whereas a graph doesn't necessarily have that ordering. And so the example that I give for a graph is the cities on the interstate highway system. And so you can get from city A to city B by more than one route, and possibly by many routes, all of roughly equivalent quality or length or whatever. And so there is no hierarchy unless you prescribe to the idea that that some cities are better than others whenever you're visiting them or whatever. But even still, like it doesn't really meet the idea of a lattice or a tree or anything like that. Okay, and then so those are graphs, and we'll be coming back to those. Okay, so the next concept that I wanted to go over was operating systems, and so it is in itself a course worth studying. So we're going to try and squeeze it down to just a few minutes, and then move on. So we'll see how much we're actually able to do here. But okay, so as you may well know, it's possible to load to install different operating systems on your computer. So if you're a Windows user, then you can have different versions of Windows. If you're a Mac user, you can have different versions of Mac OS. Linux, the same thing, different distributions of Linux and so forth. And so it's also possible to have multiple boots or multiple operating systems, and so you have a bootloader that kind of helps you out. And so how is that possible? Well, whenever you install, if you install Windows, it basically does everything for you, and I imagine Mac would be very similar. But if you install Linux, you kind of have to do a little bit more with individual effort. So you break up your hard drive into multiple partitions, and so I believe you can have 3 physical partitions, and then you can have multiple logical partitions. So on Windows, like whenever you get a new drive letter, it represents like a new hard drive, but that correspondence in Linux isn't necessarily the same thing. So whenever you get a new hard drive, you get a new device, and so you'll have like /dev/HDA and /HDB or whatever, and so but each hard drive will itself be subdivided into these smaller chunks, and the very first sector on that hard drive, the very first thing that it would load, if it's going to host an operating system, will be the boot partition. And so enough standards and practices have been developed around personal computers that the motherboard, which the processor sits on top of, and the memory sits on, and the hard drives connect to, and the power supply connects to, and so forth. It has its own mini operating system called the BIOS, and the BIOS is basically run by like a watch battery or whatever, so that's how it stores its memory. And so it allows you to save boot order, and and this basically tells the computer where to look for an operating system. So if you want to boot from a USB stick, then you have to go into the BIOS and you have to select that the USB is both capable of hosting an operating system, and it has priority over the hard drive, and so forth, right? So this little mini operating system that lives on your motherboard tells the computer, I mean, it is the computer, right? But it decides where to look for the operating system. And then on the hard drive, or the USB stick or whatever, there will be a 10 megabyte partition, and typically no larger than 10 megabytes. And this is like 20-year-old knowledge or whatever that I'm trying to recall, so forgive me if I'm mistaken here, right? But it has 10 megabytes to basically include all of the instructions that it needs to load the actual operating system. And so if you have a bootloader, then it would go in this 10 megabyte partition, and then that would include all of the information that it needs to load Windows or Linux, or if you're hosting multiple distributions on the same machine, then it would know where to look for all of those, and it would all get stored in this first 10 megabytes. And then from there, it actually loads the operating system into memory and so forth, and then the operating system kind of does its thing. So, okay, now that the operating system is doing its thing, what does the operating system do? Okay, well, the first thing it does is resource allocation. So we had an example above where we were doing linked lists, and it was written in C. And so whenever you write something in Java or C#, you'll use the new keyword, and that'll request the memory, and then it's stored on the heap, right? And then the garbage collector will know to traverse the heap and look for orphaned data objects, and then it'll reclaim that memory and do everything for you. But in C, you were given enough rope to hang yourself, and so you had to specifically request the memory from the operating system. You had to handle the case that you didn't get that memory without an error being thrown. Actually, I think it just returns null here. You had to tell it how much memory you needed. Like, you can't just specify the object, you had to specifically request it. And then you had to cast the type and so forth, right? And so a lot of this is transparent now, but here you could see an example. So we want an object, or we want to create enough memory to hold a character pointer, so an address in memory. On a 64-bit machine, this would be a 64-bit variable. On a 32-bit machine, it would be a 32-bit variable. It's an address in memory. Right? And then another address, so again, 32 or 64 bits, depending on the machine. And then another address. So we need 3 words on the machine. So either 3 64-bit integers or 3 32-bit integers. And so size of computes that request, and then it returns a number of bytes for a given type, right? Structured node, and then we make the memory allocation request. We malloc that specified number of bytes, and then it returns a pointer, and so we cast the pointer. Otherwise, I think it's like a void pointer. And then later, so this isn't exactly good code. We'd already found at least one error in this. We should check to see whether or not the pointer is null. So if the operating system says, no, this program is not allowed to consume any more memory, then it'll return a pointer to null, and you can't actually write to that address. And so an exception would be thrown the first time we attempted to perform some operation on this node. But you can test to see whether or not you actually received the memory allocation request, which is what we should be doing. Okay, and then you would do something very similar for other types. So if we wanted the list type, if we wanted a new list as opposed to a new node, then we would do we would make our memory allocation request for the size of the type that we wanted, which is a double list. So the operating system is on the receiving end of these requests, and it takes a look at the space allocated for that program, so where in RAM that program's memory is stored, and then it checks to see whether or not the program has exceeded whatever maximum threshold there is for that program. If it hasn't exceeded the maximum threshold and there's no memory available on the heap, it'll reallocate. It'll borrow more memory from RAM. It'll increase the actual footprint of the program, and then it'll create this. It'll satisfy the malloc request from that newly created memory or newly allocated memory block. And this has the effect of, in C programs, of monotonically increasing footprints. So even whenever you free the memory, once that additional block has been allocated for a program, it never goes back and shrinks it. And so this behavior is seen in other places as well. So if you look at log files for databases, even if you clear the log, the amount of space allocated for it never actually decreases. So occasionally you'll have these maintenance periods where you have to take the database down and essentially completely drop it and recreate it so that you can get rid of this log space that's been allocated. These many gigabytes of space that aren't being used, but for whatever reason it's just not able to properly reclaim. And so anyway, you see that behavior of this ever encroaching footprint of programs in C and in other places. So just because something has been released, has been freed, it doesn't necessarily mean that the actual space that was taken up by it has been fully reclaimed by the operating system. But anyway, equal and opposite concepts here. You can borrow memory, and then whenever you're done with it, you can release the memory, you can free it. Okay, and then okay, so it handles resource allocation, and okay, so resources are more than just the memory itself that's being used by the program. The number of open files and how the files are managed whenever they're opened is also handled by the file system. So if you program in Node, or I guess in C as well, whatever, then whenever you open a file, you're returned a file descriptor rather than in C# or Java, you're returned like a file object instance. And so in those other languages, then you can just interact with it or whatever, but they're doing some stuff transparently for you, and in Node and C it's a little more apparent what is happening. So in Linux, you can actually find a location where these file descriptors are open, and so you make your open request, and a file descriptor, which is a special type of socket, is created in some directory path that you can actually navigate to, and you can see it. And whenever you need to read or write to or from the file, then it's written into this buffer, and then the operating system will take it and it'll write it to the file, or if you're reading from it, then it'll read it into the buffer, and then it'll pipe it over. It'll extract it from that buffer, and it'll move it into your program. And so it, even though it seems like all of these things are happening synchronously, like it's all happening all at once in this steady stream, it's much more jittery than that. But the computer is so fast that you don't really see all of these steps. It appears to happen, all at once. But that's what the file descriptor is. It's a location for this buffer essentially, and so it's just a serial number, and so it's given some number between I don't know if it starts at 0, but like between 1 and whatever the maximum number of files that may be opened on a system is. So I can't remember what that is, but I remember it's somewhere between like 8,000 and 64,000. So you get a fair amount, but you don't get millions and billions of files that can be opened simultaneously on the operating system. So it's you may encounter a problem where this actually eventually becomes an issue, but you're probably safe from it for a while. Just remember that there's an actual maximum number of files that can be opened at a given time. Okay, and then the other major feature of operating systems is scheduling. So I know it's fairly common to have multiprocessor machines now, or multi-core processors where you're allowed a lot of simultaneous input or throughput, but there are still more processes running than a typical machine will have processors to handle all of that action. And so the operating system, the main thing I would say that it does is it's scheduling. And so it decides which programs get to execute for how much time and in what order, like what priority. So the operating system itself needs processing time so that it can make decisions like this. It can handle resource allocation requests. It can handle incoming network traffic. It can read all of the data from these buffers and either flush it out to the devices like the hard drive or whatever that need to be written to, or to pipe it into whatever program has requested that data, either from the hard drive or from the network or from a webcam or whatever. And so the operating system is acting almost constantly. So it'll give itself priority so that it can continue to manage all of these requests. And then it has to decide which programs get to execute. And so it breaks it up into a schedule. So modern processors are pretty fast. A 3 gigahertz processor is performing 3 billion computations per second, which is almost unfathomable. So that's a fair amount of computation. So even if you're only allowed a second, you're still allowed 3 billion, load, add, move, whatever operations, logical operations, and that's a fair amount of time. But the processor also has to be pretty smart about how it's doing its scheduling as well. So we haven't really touched on virtual memory, but the processor will often, so you have however much RAM, the random access memory is available on the machine, and then the processor, if a hard drive is attached to the computer, then it'll typically borrow some space from the hard drive as well, and it'll extend its memory bank into the hard drive, and that extension is called virtual memory. And so when a program is executed less often than others, then the operating system absorbs the performance hit and it moves it to the hard drive, or these seldom run programs to the hard drive, and then it continues to interact with memory, which is typically 10 times faster than virtual memory or hard drive access, and it does its thing, and it lets those other programs run, and hopefully they'll run to completion or get to a state where they're not terribly active, and then it can go ahead and process these procrastinated programs essentially. But there are two extreme ends of scheduling that the operating system tries to avoid. And so the first one is starvation, where the operating system loads one program and it allows it to do whatever it wants for however long it wants, and then every other program is essentially starved for resources. It just doesn't get its seat at the table, and so nothing ever happens with those programs. And so if you databases can typically be pretty greedy processor hogs, and so it's possible for them to starve other operations. And then in particular, if you block a transaction, and so the database is just unable to return, then it's possible that it'll stay in memory longer and starve other resources on that same machine. And so it is possible to contrive a scenario where starvation occurs. And so that's at the one extreme end, where one process gets priority over everything else and the rest starve. So you can think of that as like the French gentry, where let the peasants eat cake, and the ruling class is well fed. And then at the other end is what's known as thrashing. And so we'd mentioned virtual memory and how slow that can be. So there's an expense moving a program to and from virtual memory. So if you're moving it into RAM, into random access memory, then it takes CPU time, and you have to wait for the hard drive to respond, and then you have to perform these swaps or whatever. And so if the processor doesn't allow enough time for programs that might actually complete, or processes that might run to completion, then it ends up with this huge backlog of processes that are requesting time, and it's instead of allowing any of them to execute, it's just constantly swapping programs in and out of virtual memory, and so that's called thrashing. And so the real world analogy to that is if imagine you're taking 21 hours as an undergraduate, and every one of your instructors gives you an exam and a quiz and a homework and then a long-term project, and they're all due within the same 1 week period. Then rather than actually getting any work done, if you're going to give them all equal time, then you're constantly swapping them back and forth between the subjects, and that mental exhaustion that you feel from context switching, from having your brain jump back and forth between the different subjects, is exactly what the operating system feels whenever it's thrashing, whenever it's trying to give a little bit to too many different requests at the same time. So okay. So file systems. I think this might actually be the last subject we get to discuss. So, okay. So the file system is actually distinct from the operating system. So it acts as this bridge between where the data is actually stored and how we as users see that data. So whenever we see the data, we see a C drive or a D drive or whatever, and then all of the subdirectories in their name form and so forth. Or if you're on Linux, you see slash and slash user or slash home slash sys or whatever. And so the file system, is kind of that translator between the persistent storage and the operating system's interface, or the command prompt, or the file explorer or whatever. And so whenever it's dealing with the hard drive, then it deals with Inode tables. And so I'd mentioned the concept of partitions on the hard drive. And so in addition to the physical partitions that get placed on the hard drive, it's actually subdivided. You can think of it like parcels of land. So whenever whenever you buy land, so if a land grant is issued by a state or whatever, then you can buy the land from the state, but typically it's already broken up into these divisions of land, and you have to buy them in integral amounts, right? So you can't say, well, I want this 45-acre plot of land, and then like, could you just extend the boundary by a foot to the east as well, or whatever? No, they're not going to do that. They've already broken it up, and they want you to deal with those sections. Now you can in turn allow some of that land to stay fallow or whatever, like however you use it is fine, but you jump in for whatever the size of that parcel is, right? Whatever the size of that division of land is, and you have to buy it in that transaction. So the same concept happens on the hard drive. So if you have a 2 terabyte hard drive, then you can't actually start a file at any one of those 2 billion bytes or trillion bytes. You start it at it's either like 1 kilobyte or 2 kilobyte or 4 kilobyte blocks, and so you're getting a block, and you start at the beginning of that 1 kilobyte block, and whether or not you use that full block, then it's still allocated to that file, right? So if you open a file, then and you write just like a single space and then you save it, then you'll see 2 values. One of them is like file size, and the other is like size on disk, whatever, that second variable or that second value. And so the size on disk will indicate like the number of these blocks, the number of these node blocks that are used. And so, okay, so the Inode table is kind of like the address book or the lookup for where a particular file is stored. So if we go back to our land parcel example, right? It's possible. So I don't know if any of you have ever defragmented a hard drive, but it's kind of what happens. So it's possible for a file to end up on non-continuous blocks of the hard drive. So in our land grant example, it's like having a ranch, but you have half of the acreage in West Texas and the other half in East Texas, but it's all the same ranch, right? And so that can happen on the hard drive, and the Inode table is kind of the reference for where to look for the different segments of the file and so forth. There are fewer inodes than there are bytes available on the hard drive, and it's because it's broken up into these segments. Or parcel is a term I came up with. That's not going to be standard, so I wouldn't look for that. But it's the concept of it. Okay, and then there's permission settings. So each file is owned, on some level, by the file owner. So typically it's whoever created it, or if the creator of the file decides to change the owner to someone else, then it's whoever it was changed to, assuming they have permission to change it to that other person. So there's the file owner. You can think of that as the file creator. There's the group. So if we had in our computer lab a discrete math group, then that would be any file. Any file created by any one of us would belong to the group of that individual, but we can choose to assign it to. We can change the group ownership to some larger concept, like anyone that's in our class, and then there's the universal owner, which is everyone that has access to the system. So there's user, group, and then everyone, and then there are 3 permissions, and these are given numerical values as well, of read, write, and execute. So for a directory, which we'll discover in just a minute, everything is a file, right? Directory execute means that you can list the contents of the directory. For a file, it means that you can run it like an application. So in Windows we have .exe files, so it's an executable file. But in Linux, there's bin files, the binary files, which are the equivalent of an exe. But they also have script files, and you can modify a shell script to be executable by adding the execute permission. And then read and write are pretty self-explanatory. And so I give an example. So this command, chmod, so we're modifying the file permissions, 764 for the file foo.txt. So this first one, I said every file is owned on 3 levels. It's the file creator, the group ownership, and then everyone else. Right? So the 7 would represent each of these privileges that they have. So the file creator has read plus write plus execute. It adds up to 7 permissions on this file. And the group, so our discrete math group for that file, has 4 plus 2, so they have read and write permissions, but they can't execute the file. And everyone else has 4, so everyone else can read the file, but they can't modify it or execute it. And then a more restrictive example over here, so chmod 700 bar.txt. So the file creator can do whatever they want, and then the discrete math group, or whatever group owns the file, can do nothing, and also everyone else can do nothing. Right? And so that's if you're securing your system, you probably want it to look a little more like this. Okay. And then, as I'd mentioned, everything is a file. So earlier, whenever we were talking about opening a file, and the operating system creates a file descriptor, so the serial number, which is a location within the file system directory path. So what it's creating when it's creating that file descriptor is a socket, and so sockets are just a special type of file, and it's just a buffer, right? And so but beyond that, like directories are also considered files in Unix or Linux systems or whatever. So you can actually edit them with a text editor, and you can see the contents of the directory and a pointer to the I guess the Inode table for the particular file that's referenced. So where that file begins, and then that file it'll contain a reference to wherever else that file has been segmented off to, and so forth. Right? But conceptually, everything that deals with input and output, so from network traffic to device interactions to streaming output or console output and so forth, to file interactions themselves and so forth, everything passes through one of these file descriptors. And so conceptually you can think of everything as some abstract level as being a file. And then we kind of discussed sockets as well. And so on Windows these are called named pipes, but on Linux it's just another one of those file descriptors. And so it's just a buffer, and the operating system does most of the work transparently to the user, and so it uses it to just kind of route. So you're subscribing essentially to these sockets, and for as a programmer or whatever. And so you opened some request either for a file or for some network transmission or whatever, and if you're using a modern programming language like Java or C# or whatever, then you get back an object, and most of this is done transparently. If you're using C or Node, then you get a file descriptor, which is again just a serial number or whatever, and then you're pulling the data out from this buffer, and you're reading it in, one chunk of data at a time, and so forth. But you can think of a socket as just being this fixed size buffer that is a space in memory that's just reused over and over again to kind of load data in, or as a staging ground for whenever you're sending it somewhere else. Okay. Yeah. And so I'd wanted to talk about networks and everything else as well, but I think that's kind of our time. Okay. So hopefully that review makes sense. Luckily it's recorded, so if you need to watch any portion of it again, you can, and I will update the notes as well. So, all right, have a good weekend, everyone, and we'll meet again on Tuesday. Thanks.